In this video we're going to take a look at PPassAB and PSearch and the similarities and differences between them. These are both initiators and they both allow particles to search around and find other particles. In PSearch's case, particles not required. You can actually use just a position input. And let's go ahead and create some particle groups to make a logical discussion here. Let's use a colors black box, which just creates a whole bunch of color groups. So for PPassAB, if we wanted the red particles to search for orange particles, we'd set it up like this. Whereas for PSearch, we're going to have red particle fed into the particle input and choose the drop down here with the orange particle. There's actually, of course, this group drop down. You can optionally use the group input here in certain situations, maybe with references or memory operator. You can do that as well. Okay, so what do these really do when they're processing TP? Well, what happens is PPassAB, the way we have it set up right now, we've got these different options here, and it's set to all. What this means is that each and every red particle, starting with the first red particle, is going to search through and compare itself with each and every orange. So that means red number 1 is going to compare with orange 1, orange 2, orange 3, etc. And then red 2 is going to compare against orange 1, orange 2, orange 3, etc. All the way through until there's no more red to be compared against the oranges. And that happens all in one time sample. It's important to know. So these options here control when that comparison occurs. Now right now it's set to all, and that means there's no distance checks, no other kinds of size or shape collision checks. It just every time sample, every red's going to compare against every orange. And that can be quite a bit of sampling, and so that will actually end up weighing you down a fair amount. So you're going to want to try to control that if you can get away with it. We can either test by distance and limit it so that the distance between these two particles has to be 10 units or less. This, of course, is in world units. And what happens is, actually, let's go back here to the all option. We want to talk about these outputs. What happens when every red compares against every orange is these outputs become active. So if we actually, let's say visible all, every time a red particle compares against an orange particle, any of these outputs will be able to fire and be true. Not just fire and be true, but it'll actually feed out its information. If we set the distance to 10, then of course that red particle, who is within 10 units of an orange particle, that red particle is going to fire, and then coming out of the B particle group, for group B there, this orange particle who is within that 10 units is also going to fire and send out its info. Now of course we can limit that and say only the nearest within 10 units. And so if there were 5 orange particles within 10 units of the first red particle, then the red particle is going to fire, and then only the one nearest orange particle is going to fire to that B particle group. Okay, here's the other thing. If you turn that off, what happens is still within 10 units there's only 1 red and 5 oranges. What's going to happen per particle? So the red's going to fire, and then orange 1's going to fire, and then red 1's going to fire again, orange 2's going to fire, red 1 fires again, orange 3 fires. So these comparisons are going to be coming out for each particle comparison, and of course that's all in one time sample. Okay, PPassAB is kind of nice. It has a couple other options that PSearch does not, and that is the particle size and the particle shape collision. So particle size is actually, I believe it's a radial or spherical representation where the particle's size, if the size of red and the size of orange, I'm pretty sure it's in spherical terms, if those overlap at all in space, then these outputs fire true. Whereas if we say particle shape collision, then the red particle shape has to intersect and overlap the orange particle shape in order for both of them to fire out. Okay, and that can be quite expensive time-wise to do all that checking, but it can do some pretty interesting effects. It will allow you to detect when particle shapes do collide without actually having to use a shape collision. So it will kind of allow them to interpenetrate without having to worry about them bouncing off of each other. Kind of a special case there. Then of course it also has this invert option. So if the particle shapes are not colliding, then they fire out true. If their sizes do not overlap, then they fire true. And of course if the distance is not within 10, if it's greater than 10, because of that invert, then they fire true. Okay, so you get the picture. Okay, so PPassAB, there are some difficulties and problems with it too, and we just want to talk about that real quick. One of the difficulties is that even though you have this on input and you can limit when this comparison happens, sometimes, like if you have it set to all and you have a lot of particles, you're talking hundreds or thousands or hundreds of thousands, you're going to end up with a lot of comparisons going on, and that can be quite slow. So one of the nice alternatives to PPassAB is PSearch, and PSearch also has an on input here, so we can control when the search happens, say maybe at particle birth. So when the red particle is born, each and every red particle at birth is going to do a PSearch for orange particles within this radius. And PSearch is really distance specific, radius specific here. It's always kind of limited by this distance. If you want, let's say you have a pretty big scene size and you always want all the red particles to find every orange particle, similar to the all option here in PPassAB, then you're going to want this radius here to be pretty large. You can crank it, way up. Okay, now PSearch, PSearch, let's get this out here. Like we said, it has some handy options here where we can actually pick the group dynamically, who it's going to be searching for. So if you had maybe let's get a memory in here first. Memory with the group. Don't you wish these were all alphabetized? Interesting. We don't have particle group here. How about that? Well, we could script that if you wanted, or in our other case here, what we'll do is a get reference, where we could actually query that reference particle group. Not quite the best example there. But of course we also don't even have to have red particles. Let's say you had a shape collision further down in your scene here, and there's a collision between a couple particles, and we're going to use a memory to store the again, please alphabetize these, position of that. We can store the position of the collision for each and every collision, and then we would want this rule to be afterward here, and we could have that memory feed directly the position, that collision position, into this PSearch. And so every time there's a new position value coming out, PSearch is going to fire off, and it's going to search for orange particles within that radius. Okay, and of course the outputs here between the two are a little bit different. PPassAB, it basically gives you all the particle properties. Not only does it give you the particle properties, but let's create a data channel here. It also gives, PPassAB also gives you the data channel access, which is pretty handy. Fortunately, there are some ways around this that we usually do. where we'll make a rule where any particle group who has a data channel, we can just set that up and directly feed that into a memory operator. So that data channel, no matter what, is always being stored in memory. In which case then you can use your PSearch, and for each and every found particle you can access its float data channel value that way, since there is no read data channel operator. There's only the set data channel. Okay, so PSearch has some different outputs. It allows us to output something kind of like only the nearest. It'll output the nearest particle ID that it finds within this range. It'll output and tell you what that distance is right away, what the furthest PID is, what the furthest distance. And this one here, found PIDs, this is a very special one. And let's go ahead and just set up a little situation where a red particle at birth is going to be searching for orange particles within 10 units. So what's going to happen is, each and every red particle at birth searches around for orange particles within that radius, and every orange particle that it finds, it's going to fire off out of here, all in one time sample, but one after another. It's not like all at once in one big array. It's basically sequentially, one after the other. Okay, some other data that it outputs, it'll tell us the found, this should be indices, but indexes. So this will actually tell us the current integer number, and it's zero based, of the total count that it finds. So if it finds 20 orange particles, our found count's going to be 20, but our found index, it's going to start off and it's going to be 0, 1, 2, 3, etc. And that's going to fire off, sequentially as well, and it's going to match that found PID. Each one of these found distances, these are also kind of sequentially one at a time. Okay, then it also has a couple really nice outputs here at the bottom. The found average position, which basically wherever your 20 orange particles are, it's just going to average their positions and give you that average position, as well as the average velocity. So these two things are really good for crowds and other kinds of group behavioral dynamics. Okay, so that is about the long and the short of it. We're going to go ahead and create a sample file next using this kind of scene layout here to show some of the differences between PPassAB and PSearch.